chapter 3 today, trying to do a recording. I'm not able to make it to campus today. Definitely can't do a live stream from my house. I have satellite internet and it's raining, so just trying to get something in. Hopefully it's going to make some sense. Today we're talking about only discrete things. So discrete are things that you can count, and it's a finite number usually. So, but not necessarily. It could be infinite. But we'll just usually deal with finite discrete things. So first of all, we just got to talk about some terminology here. The first thing we want to talk about is a random variable. And a random variable is just a way to take those events in your sample space and map them to a number. So for a random variable, it could take something like heads and map it to 0, and then tails, it could map it to 1 or something like that. But a random variable is just a rule or a function. Even you could say it's a function that maps outcomes in the sample space to numbers, either an interval, like if it's continuous it would be an interval, or if it's discrete it's some number and then some number plus 1 and then some number plus 2. It could be whatever. So it just depends on what the outcomes are, what you want to map them to. If there's a natural number already associated with it, like a die roll, if you roll a die, there's already a number associated with that. But with like a coin flip, heads or tails, there's no like intrinsic number associated with heads and tails. So you can arbitrarily choose like 0 or 1. Now, the notation, the capital X, if you ever see capital X or a capital letter, that typically means the random variable or the function that is going to map events to numbers. The lowercase x right here, I've just made a note here, the lowercase x is any value that the random variable could take. Like for a die roll, like x is the number that comes up on a die roll, capital X. The numbers that little x can take are numbers between 1 and 6. So basically little x represents a value that the random variable capital X can take. So just some notation, some terminology we're trying to get going here in this chapter. One thing I really want to emphasize is that in this chapter, we are only worried about discrete random variables and discrete things. We're going to talk about continuous stuff in chapter 4, but this chapter is all about discrete stuff. So let's look at this example. It says checking a fuse to see if it is defective or not defective. Well, the sample space could be defective or not defective. Now we pretty much have the freedom to choose. Do we want defective to map to 0, or do we want defective to map to 1? We could map it to any other two numbers, honestly. We could but 0 and 1 are kind of the go-to if you only have two outcomes. So you could map it to 1 and 2, or you could map it to -1 and +1, but we just pick 0 and 1. So that would be an example of what your random variable could do. So here's your random variable acting on the defective event, and it maps it to 0. Here's the random variable mapping the non-defective event to 1. So it's really just a function that takes your events or your outcomes and maps them to numbers. So another example is we could have fuses and we check one by one until we find one that is not defective. So the sample space would be, well, the first one is not defective. So x of n would be equal to 1. So that would be like a natural association. This first one was non-defective. Now, you could have a defective one and then a non-defective one. Then you could have an outcome of 2. It could be defective, 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 and the fourth one is non-defective. So then it would naturally map to 4. You would need 4 fuses to get the first non-defective one. So that's a natural association with a number. So basically you're taking these outcomes. How many fuses does it take before you get to a non-defective one? Well, maybe it takes 4, and then you've got your non-defective. Well, that one could continue until you reach, all of your fuses. If you have infinitely many fuses, which you can't, then it would be, going really large. Now, a note is that a random variable that takes only 2 values, kind of like this one up here, defective or non-defective, or heads or tails or something like that, like 0 and 1 are your numbers that you map to, then you call it a Bernoulli random variable. So that's something you want to remember, is because we're going to use this terminology quite a few times. We're going to talk about Bernoulli random variables, and that's really just any random variable that only takes 2 values, like 0 and 1, or whatever you define it to be. Or if there's some kind of natural association with the number already, then you would say, okay, That's your Bernoulli random variable. Now, like I said, in this chapter 3, we're only going to focus on discrete random variables. We're not going to focus on continuous random variables. In chapter 4, we will focus on continuous random variables. So that's anything that maps to an interval of the real line. So basically, like time and things that are continuous, things that you measure, those are continuous random variables, versus things that you count, which are discrete. We'll come back to this last line here, this note, when we get to chapter 4, so don't really worry about that right now. So 3.2, the probability distribution for discrete random variables. So the probability of event A is the probability of random variable x taking the value little x. So if A is your event that x takes on the value little x, what's the probability of that event? So that's kind of what we're trying to answer in this chapter, is talking about distributions of random variables and how is the probability distributed among the possible outcomes. So that's what a probability distribution tells us. How is the probability distributed among the possible values of x? Question is, what is the likelihood of an x value or a set of x values? That's what a probability distribution tells us. How is the probability distributed to the x values that you can actually take? Well, it's given by a function, p, little p. So little p is going to be the way we distribute probability among the x values. For example, it's usually given in a chart like this if you have a finite number of x values that your random variable can take. This example says, let's say we have 6 computers in a lab. The random variable x is the number of computers that are in use at any given time. Note, computers are discrete, right? You're either using a computer or you're not. You're not using half a computer. Well, I guess you have to like say, okay, what's a computer? But really, I mean, you just have like a station that somebody can sit at in a computer lab. You don't have like a keyboard. You don't have just a monitor in a computer lab and say that they can use the monitor without using anything else. So it's just like a whole computer. So it's a discrete thing. So we're going to model it as a discrete random variable. It's the number of computers that are in use at any given time. This distribution says that the probability that 0 computers are in use is basically 0.05. So 5% of the time, no computers are in use. The next one says 10% of the time, exactly 1 computer is being used. 15% of the time, exactly 2 computers are being used. 25% of the time, exactly 3 are being used, etc. 20% of the time, exactly 4 are being used. 15% of the time, 5 are being used. 10% of the time, 6 are being used. So, question 1 is, what is the probability that 2 computers are being used? Well, that's exactly little p of 2, which is 0.15. The second question is, what is the probability that at most 2 computers are in use? Well, you don't want to be more than 2, you want 2 at most. So that could be 0 or 1 or 2. Those would all be disjoint events. Exactly 0 is disjoint from 1, and that's disjoint from exactly 2. So these are all disjoint. So you just add them together. Probability that x equals 0 is little p of 0. Probability that x equals 1 is little p of 1, and probability that x equals 2 is little p of 2. Add those together. That's basically these 3 right here. So that's 0.3. What is the probability at least 3 computers are in use? Well, the probability that at least 3 computers are in use is probability that x is greater than or equal to 3. Well, the complement of that would be 1 minus the probability that x is less than 3, which would be 1 minus the probability that x is less than or equal to 2. Because it's a discrete value, the thing below 3 would be 2. So if we're below 3, then we have to be less than or equal to 2 because it's discrete. Well, we know probability x is less than or equal to 2 already. That's 1 minus 0.3, which is 0.7. So 70% of the time, basically these 3, this is 0.7, this is 0.3. 70% of the time, there are at least 3 computers in use. Now, this one, what is the probability that x is strictly between 2 and 5? Well, since it's discrete, that means probability that we are greater than or equal to 3, but less than or equal to 4, because it's discrete. Right? If I'm discrete and I'm greater than 2, then I have to be at least 3. If I'm less than 5, I have to be at most 4. So this is going to be the 3 in the middle. So that's going to be 3 plus 4, or sorry, the 2 in the middle. So it's probability of 3 plus probability of 4. Add those two in the middle together, that's 0.45. So that's a good example to look through. It's all discrete. It's so important to know that this is discrete. And when you have discrete events or discrete outcomes, then you have to when you're strictly greater than something, you have to go up to the next value. So if you're greater than 2, then you're at least 3. And it's discrete. So basically add 1 in discrete. Now, a probability distribution for a discrete random variable has a very specific name. We call it a probability mass function. So it's a probability mass function of a discrete random variable x. Is defined for every x by p of little x is equal to the probability that your random variable capital X takes on the value little x. So just like the last example, so recall the table. Sometimes if you have a finite number of outcomes, the probability mass function is given in a table just like this. So this is our PMF from the last example. So sometimes it's given as a PMF just like that. Sometimes it has like a formula associated with it. If it's not like something you want to write out or whatever, maybe you have to give it in a formula. We'll see some examples of distributions where you have to use a formula. But sometimes it's just given in a table because there's just a handful of outcomes. So let's look at some properties of a PMF. The probability of each outcome is always greater or equal to 0. That's kind of just like an overflow from what we already know about probability. We know it's got to be positive or non-negative. And then the sum over all outcomes of all the probabilities has to be 1, just kind of like the sample space. Like all outcomes in the sample space, all their probabilities added together have to add up to 1. So that's just kind of a natural connection from what we already know about probability as well. All right, so now let's look at another example of the probability distribution for discrete random variables. Example, 6 lots of components are in storage. Each lot has some defective components. Lot 1 has 0 defective components. Lot 2 has 2. Lot 3 has 0. Lot 4 has 1. And lot 5 has 2. Lot 6 has 0. One lot is selected at random. So I'm randomly going to select a lot and ship it to a customer. X is the number of defective components in the shipped lot. X equals 0, what's the probability that we picked a lot that has 0 components? Well, how many of the lots have 0 defective components? 3 of the 6 lots have no defective components, right? This one, and this one. 3 of the lots, 1, 3, and 6, have no defective components. So 3 out of 6, so 0.5 is the probability of sending a lot to a customer with no defective components. Now, what's the probability we send a lot with 1 defective component? Well, that's only one option. There's only one lot that we could send that would have a defective component, and that's the one right here. Basically, if we send lot 4, then we might send, or we would be sending 1 defective component. So 1 out of 6 chance of picking that lot, basically. And then what's the probability that we could select a lot that has 2 defective components? Well, that's these 2 right here. So I could send lot 2 or lot 5, and I would be sending 2 defective components. So a 33% chance of sending 2 defective components to a customer. So the probability distribution function then over here, this is our PMF right here. So this PMF is described by this table or this function, piecewise function, and it's only for x equals 0, x equals 1, x equals 2. We cannot send anything else. We can't send -1 components. We can't send 3 defective components because none of our lots have anything other than these number of defective components. So that would be our probability mass function for this set up for this example. Now we can visualize that with a histogram. We have the probability here of 0 defective components, probability here of 1 defective, here of 2, and then we could just basically do the same thing except without the whole box. Just draw like a little line for your probability. Alright, so a probability distribution that takes on 2 values, we know that's called a Bernoulli random variable. Then you might have some parameter A that defines the PMF. Like for a coin flip, it's basically A is 1/2 or 0.5. So each outcome then has 0.5 probability. But it could be unequally likely, like in a Bernoulli random variable. Like for example, you could say like your event could be getting a 1 on your die, and then anything other than 1 on the other side, basically saying like your 2 outcomes are either a 1 or not a 1. So basically you say true or false, or this event or its complement. Then you could say A in that case, probability of getting a 1 would be 1/6, and probability of getting anything else would be 5/6 if you were to roll a die, a 6-sided die. So A is called the parameter of the PMF. The collection of different PMFs that can be obtained is like a family of distributions, a Bernoulli family of probability mass functions. So we're going to do this quite a bit when we talk about some more distributions. We're going to have things that we have to define as success or failure. And so there's 2 outcomes, and we have to know what the probability of success is. And that's basically going to be little a. So we're always going to be using these Bernoulli random variables in the future quite a bit. So the last thing I want to cover today is a cumulative distribution function. It's the addition of the probabilities up to some particular x value. So the CDF, capital F of x, of a discrete random variable with probability mass function little p is defined for all x as the sum for all y less than or equal to capital X of the probabilities up to that point. So it's an accumulation of probability. So it's an accumulation of probability up to that x value. So notice right here, the thing we want to highlight is this less than or equal sign. So note this less than or equal sign right here. So we can take a PMF and derive or collect the probabilities to get the CDF. We call it the cumulative distribution function. So we basically just add the probabilities together. So let's see. Let's look at this example here. We have, okay, probability that x equals 0 is 0.5. Probability that x equals 1 is 0.167. Probability that x equals 2 is 0.33. So that's our, actually that's our last example. We derived this PMF from the number of defective components in a lot or whatever that we were sending. So now, what is the probability that x is less than 0? Well, if x is less than 0, we know that there's no probability accumulated yet. Well, if x is greater or equal to 0 but less than 1, then I've only hit this x value right here. So my probability up to that point is 0.5. Now, if I go to x equals 1, I add this, and I get 0.666, repeating, or 0.667. Now, if I add the last one, x equals 2, once I go past 2, I've accumulated all the probability. So no matter where I go after that, I've accumulated all the probability. So all probability accumulated. There's nothing else to add because it's 0 after that, so we've accumulated all the probability after we get to x equals 2. That's a CDF. And if you were to plot, the CDF, well, before you get to 0, you've accumulated nothing. Once you get to 0, you've accumulated 0.5. Once you get to 1, then you accumulate 0.66. You get 1.167 more. You add that, you get 0.66 repeating. And then once you go past 2, you get to 1. So that's our cumulative distribution function if we graph it. So We'll go over one more example here, I think, and then let's see. Yeah, I think I just want to go over this example, and then we'll probably stop here. So let's look at this example. This example is going to be X is the number of births in a hospital until a boy is born. So let probability of boy be little p. So the probability of 1 would be probability of boy, which is little p. What's the probability that it takes 2 births and then the boy is born? So basically like girl and then boy. Probability of girl and then boy would be probability of girl times probability of boy, because they're independent. Man, this is killing me. Alright, so this is going to be 1 minus probability of boy times probability of boy, which is 1 minus p times p. If it's 3, so basically 3 births, and the third one is a boy, you got girl, girl, boy, so 1 minus p, 1 minus p, p, so 1 minus p squared times p. So basically, the general formula is probability of a certain number of births until a boy is born is 1 minus p to the x minus 1 times p. So basically p is the very last one, which is a boy, the rest were girls, and x minus 1 were girls, and the last one was a boy. So that would be your distribution function. So this is more of a general thing that you can't write in a table because, I mean, technically it could be like infinitely many. So let's try to derive. So once we have the PMF, we can start to try to figure out what is the CDF for this function. So the CDF is going to be the addition of all these values. So all these values are going to be from 0 all the way up to some x value. So that's from 1 to x, summation, y equals 1 to x, 1 minus p to the y minus 1 times p. So that's going to be, well, p can come out entirely from the summation. However, anything with a y cannot come out of the summation. So 1 minus p to the y minus 1. Add all those together. Add all those together. That's going to be, we've taken out the p. Then this summation, we can pull it over here and we can re-index this summation. Say basically like a u substitution for a summation versus an integral. We change the bounds. We make n, we're going to make n y minus 1. N is going to go from 0 to x minus 1 now. If we basically take these bounds, 1 goes in here for y, n becomes 0. Y equals x, n becomes x minus 1. Now, there's a nice formula, it's called a geometric sum formula that we use right here, and basically a is equal to 1 minus p. So we use this geometric sum formula right here to get this answer right here, which is going to be p times 1 minus p to the k, or sorry, to the x, over p, which is just going to be 1 minus p to the x. So that's how they get this answer right here. So that's basically that's the CDF if x is between 0, or x is greater than 1, sorry. So that's the CDF if x is greater than or equal to 1. And here x is the largest integer less than or equal to x. So if like you put in x equals 1.7, you would say that x would be really just be 1. So 2.7, the bracket notation would mean 2. Because you can only plug in integer values, like your x is the number of kids, right? So you can't plug in like decimal parts of kids. So that's kind of the idea. The cumulative distribution function can plug in different values, try to figure out what is f of 5, what is f of 10, and you get basically 1 right there. So that's kind of the idea. Let's stop here. I think we'll go into how to get the PMF if we know the CDF next time, and then keep going with expected value and things like that. So we'll go through that next time, but we'll stop here for now.